So my phone ran out of memory as I was making that last video, so it got cut off. We were talking about error. We said that we didn't account for error resistance. Right. Another one here is the value determined for this acceleration of gravity is lower than what we expect in the first experiment. We would say also that this experiment doesn't say anything about that pulley not being frictionless or massless, so we could talk about didn't account for the moment of inertia, or it doesn't, they're saying that this is a smooth horizontal table, but smooth doesn't necessarily mean frictionless. So all of those three things, air resistance, friction, or the moment of inertia of the pulley, would skew the data in such a way that would give you a lower value to the acceleration due to gravity. So there you go. Those are three ways of doing it. We want to think about that sort of thing when we're doing error. So what did we learn from this problem? From the top, we learned no components. We learned when doing equation work, we want to have premise statements. We learned the linearization of an equation. So you develop an equation that shows the link between the things that you have data for. And then you organize them so you can see some sort of y equals mx plus b. Whatever's on the y, you put you make a new column for, or in this case, row for. And then whatever's on the x, you make a row for, you calculate the data, and then you plot it so you get a linear function. Use a straight edge for your best fit line. Remember, it is a best fit line. And then when you're finding your slope, or if it's finding areas, whatever it is, something about what you've done up here is going to allow you to use the graph in order to calculate something. Here, I made sure to use the points on my best fit line. I plugged in with units. Super important. I stated explicitly what the link was between the unknown thing and what it is that I was looking for. Next, on the higher, lower, equal to sort of thing, even if they tell you not to use equations, what they mean is don't solve it. But there's nothing wrong with citing equations and citing proportionalities so that you can talk about as this thing increases, that thing decreases, sort of proportional reason logic. And you notice I use that as the basis for my argument here. And then when they ask you to do error analysis, you want to think about, first off, would friction or air resistance mess things up? Second, you want to think about, are there things that they told you to ignore in the problem that you really probably ought not ignore because they would have an effect? Then, when choosing amongst all those things, make sure that what you are doing is being able to explain why that thing would skew the data in the way that you're talking about. So that is the typical experimental problem.